Hi, Astronomy. This is part 6 of the chapter 13 slides. In the last part, we learned about the different spectral types and two of the heroes of astronomy from the late 1800s to the early 1900s, two female heroes. So if you're looking for early female heroes in STEM, those are two good ones to look at. So in this part, we'll continue with the spectral types and learn a little bit more about how we measure different things about stars. So let's get started with that. So who was it? So these are questions about the two heroes we learned about last time. So who was it that simplified the very excessive 17-letter stellar classification scheme down to 7 letters and then reordered them to O, B, A, F, G, K, M? That is Annie Jump Cannon. So yeah, I always go into this story to explain why we have a 7-letter system that's based on letters and yet is so far from the way the alphabet works. The story is historical and a little bit messy. That's how it works. So who came along a little bit after Annie Jump Cannon? They did work together at the same time, but the second person's career started later and ended later. So who was it that discovered the physical basis of this system? That is Cecilia Payne-Gaposchkin. So if you haven't watched this video, I'll link to this video again in the description to, my own video here. It's worth watching. Cecilia Payne-Gaposchkin, very wonderful, important person. And again, I'm always in awe of how at one point, she was the only person who knew what stars were made of. I just think it's neat that to be the only person on Earth to know a thing, and then eventually everyone knows that thing. Well, not everyone. The smart people, the people who take astronomy, know that thing. So the star spectral type is determined by the lines in its spectrum. So again, this is why the system's a little messed up. Originally, when they started the Draper catalog, it was based on the strength of the hydrogen lines. So if you had the strongest hydrogen lines, you were A. The next strongest hydrogen lines, you were B, and so forth and so forth. So here you can actually see, the different strengths of the lines and how that works. So hydrogen lines are weak in O stars, O's being the hottest. So they're there, but they're fairly weak. They're strongest at A, they're a little bit weaker at B, and so forth down the alphabet. And then they are the weakest in the K and M stars. So if you're looking at the hydrogen lines, very, very faint in these guys. So remember, the strength of the lines you see is based largely on the temperature of the star you're looking at. So O stars are the hottest of the stars. They are so hot that most of the hydrogen in those stars is just completely ionized, meaning there's so much energy there that the electrons are completely ripped off of the hydrogen molecules. So you're not going to have hydrogen making transitions from a high level to a higher level if all of the electrons are already ripped off of the stars. So you're not going to get the absorption lines for hydrogen in those stars. You'll get different ones, but not those. Or at least not very strongly. A stars are cooler than the O stars. So being cooler, not all of the hydrogen are completely ionized. And in particular, you have enough of the hydrogen in the second level so that when it gets hit by the incoming photons, they can jump up to the third level, the fourth level, the fifth level, etc. So that is why A stars have the strongest hydrogen lines. They're kind of in the middle temperature-wise. They're not the hottest, they're not the coolest. And if you go all the way down to the coolest stars, the Ks and the Ms, so remember these guys have the weak hydrogen lines. I keep focusing on this one. It's just kind of the most apparent one to me. You don't have very strong hydrogen absorption lines because K and M stars are so cool that most of the hydrogen is just in the first level. So if all of the electrons are starting in the first level, there aren't many starting in the second level to jump up from 2 to 3 to 2 to 4 to 2 to 5. So that's why you're going to have weak hydrogen absorption lines, at least the ones that start at level 2. So these K and M stars are actually cool enough to allow molecules in their atmospheres, and that causes them to have very complex spectra. So if you look at the K and the M, especially the M's, you see there's a lot of stuff going on. So yeah, why does temperature relate to molecules? If you took chemistry, molecules, the chemical bonds. Sorry, I should have thought of how to explain this. There's a certain amount of energy required to break a chemical bond. Well, if the star is very, very hot, then all of the molecules have that energy, and so all the atoms have that energy, and so those bonds are going to be broken. So you're not going to form molecules in very, very hot stars. But your coolest stars, the Ks and the Ms, and there will be cooler ones than that, are cool enough that you actually can have some molecules forming. So the actual reason why, if you have molecules, they can absorb wavelengths in different ways because the stars can now rotate. They can oscillate in different ways that a simple atom can't do. So the point is, coolest stars, you can get some molecules forming. So titanium oxide, for example. So just let me point this out again, that hot stars produce more violet than red light, and cool stars produce more red than violet light. Can you see how that works by looking at this whole picture here? Hopefully you can notice that if we're looking at the hottest stars, they're very bright over here at the violet, and they fade a little bit towards the red. Whereas the opposite is true of the cooler stars. The coolest stars are brightest in the red, and they don't put out as much violet light, so they're dimmer at the violet. So, Wien's law, black body radiation, it's back again. So here's a whole table going over the different types and the highlighting the features you will see in the spectra of stars of the different spectral types. I noticed too that anti-jump cannon system had 7. Oh, be a fine girl, kiss me. There's actually 2 more classifications that are even cooler than that. So these would be the very coolest stars, L and T. Don't worry about these guys so much. Just stick with Oh, be a fine girl, kiss me. Now, let me point out that in the coolest stars, you can actually have water molecules in their atmosphere. So that's interesting. So how do we measure stars' motion? We talked about the Doppler effect earlier in the year. So this is if you hear a car coming towards you and then driving past you, it sounds like, that's the Doppler effect with sound. So you get a similar effect with light. If the source is moving towards you, the frequency of the light goes up. With light, we don't usually talk about the frequency. We usually talk about the wavelength. It turns out if the frequency goes up, the wavelength goes down. So if the source is moving towards you, it's going to have a shorter wavelength, which we call blue shifted. And if the source is moving away from you, it will have a slightly longer wavelength, which we call red shifted. So we've dealt with the Doppler effect before. So we measure a star's motion using its Doppler shift, at least some kinds of motion. So if the star is moving directly towards you, and some stars are, those stars are called blue shifted, which means when you look at its spectra, you see the certain pattern of lines, and you can figure out that star's spectral type, but the lines are going to be shifted a little bit towards you. So at whatever wavelength you expect, that particular hydrogen line to be at, it's going to be slightly shorter. So the line's still there, but it's in a slightly different place. It's shifted. We call this blue shifted. If the star is moving away from you, then we say that star is red shifted. So you see the right pattern of lines, you know what that pattern is, but it's shifted to slightly longer wavelengths in that case. So you can only measure certain types of a star's motion. Basically, you can measure what's called the radial velocity. So you get the Doppler shift if the star is moving directly towards you or directly away from you, or at least if part of its motion is towards you or away from you. That's what radial velocity is. Whereas if you're looking at the star and the star is moving, in one direction to the side, or it's moving up or down or anything like that, you won't see a Doppler shift in that case. So the Doppler effect is not good at measuring those. That's called transverse velocity. But it is good at measuring the radial velocity, the velocity directly towards you and away from you. So there is a formula for measuring the Doppler shift. we're not going to go too far into it. This is the non-relativistic formula for the Doppler shift. But yeah, basically, when is the Doppler shift positive and when is it negative? So when it's positive, that would mean that the wavelength seems a little bit longer than you're expecting it to be, and when it's negative, it seems a little bit shorter. Well, it will seem a little bit longer, meaning delta lambda will be positive when the star is moving away from us. So its wavelength is getting longer. That's what redshift is, and delta lambda will be negative when the star is moving towards you, because that will make the wavelength seem a little bit shorter. So delta lambda, the change in the wavelength, is negative. The wavelength that you're seeing is a little bit less than you thought it should be. So yeah, sorry. Here's the non-relativistic formula for Doppler shift. There's a different formula to use, which we barely need to know this one. We don't. I mean, on the test, this wasn't even really on the test. Just know that we use Doppler shift, and if it's moving away from you, it's red shifted. If it's moving towards you, it's blue shifted. But anyhow, this is the non-relativistic. If stars are moving some significant portion of the speed of light, you have to use a different formula. It's more complicated. Physics 2 students, yeah, they would like that one, but we're not going to deal with that one. So yeah, here's the Doppler shift thing again. I went through a whole math problem of figuring this out. Well, I'll go through it quickly here. So you're looking at a star with your spectrometer. You notice that it has an absorption line of this, 656.380 nanometers. So you know that a non-moving source of hydrogen has an absorption line, or possibly an emission line. It has a line at 656.280. So how far is the star moving relative to us, and in what direction? Well, compare these two wavelengths. You're expecting hydrogen to have this one. It actually has this one. So the wavelength is a little bit longer. So delta lambda is positive. So that means it's moving away from you. So here's the math for all that. Yeah, you take what you got, you subtract what you expected, and that gets you a difference. In this case, the difference is positive. You plug the difference into this formula, the change in wavelength of the wavelength you were expecting, then you compare it to the speed of light, you do the algebra, you figure out this particular star is moving at 45,700 meters a second away from you. So, yeah, fast. That's 45 kilometers. It's almost 46 kilometers a second, but not close to the speed of light. So yeah, that's how that works. So when we take our Doppler measurements, it turns out that pretty much all the stars are moving, and those stars that are near the sun are moving in about the same direction as us. So about 200 kilometers per second around the center of the Milky Way. So this is an artist rendering. We don't have an actual picture of the Milky Way that looks like this because we're stuck in the middle of the Milky Way. You can't see the forest for the trees. It's that idea. So we're here. So yeah, most stars are going, stars that are near us are going around, I guess we're going around this way, at about 20 kilometers per second. I'm sorry, about 200 kilometers per second are going around the center of the Milky Way like that. So they're not all moving in lockstep. There is a separate motion on top of that of about 20 kilometers per second. So yeah, if we're here, we're looking at a star that's right here, it's probably going at about the same 200 kilometers per second in about the same direction, but it might vary a little bit. That's what this 20 kilometers per second is. So it might be going a little bit faster or a little bit slower or, towards it or away from it, things like that. But yeah, most stars near us are doing about the same thing. So quick review. What determines a star's spectral type? The lines in its spectrum determine its spectral type. So Annie Jump-Cannon, she was the one who reorganized that complicated 17-letter system, got it down to 7, and put it in the correct order. And then a little bit after her, a colleague of hers came along and figured out the physical basis and why this actually makes sense. And that person was Cecilia Payne-Gaposchkin. Very interesting person. On the topic of her being an interesting person, I read that book, The Glass Universe. Turns out, if you know the classical music, there was, I think his name was Holst. who wrote a bunch of pieces of music and named them after the planets and all this stuff. Cecilia Payne-Gaposchkin actually studied under Holst at the violin. And Holst wanted her. She was apparently very good. Holst wanted her to, pursue music as a career. She decided she would rather pursue astronomy. And it turns out, this is sad, later when she got hired at Harvard, there was a screw up with her paycheck, and she had to sell her violin to make ends meet. So kind of sad. So how do we measure a star's velocity towards us or away from us? We do that using the Doppler shift, the Doppler effect. So if the star is moving towards you, it's going to be slightly blue shifted. If it's moving away from you, it's going to be red shifted. So what do we call that star's motion that is either towards us or away from us? That is called the radial velocity. So you can use the Doppler shift to measure radial velocity. The transverse velocity, if the star is moving to the side or if it's moving up or down relative to you, the Doppler shift doesn't work for that. We have to measure that a different way. But if the part of its motion that is either towards you or away from you, you can measure that with the Doppler shift, which we like a lot. And that's it for this part. Hopefully you found that helpful.